Hello, everybody. I'm going to talk about deep dive into our Go binary. But before I start talking about Go binaries, I want to introduce myself and explain why I'm talking about this. I'm a software engineer in Mattermost. Mattermost is a communication platform similar to Slack, open source. Very interesting. It's writing in Go. Check it out. You can see the code because it's open source. But I'm telling this because my main work is to write APIs and React code. So I do not work in the compiler or the linker or anything near that. But I'm a very curious engineer. And one of the questions that I always ask myself is, why in the hell a hello world takes almost 2 megabytes? So what is there? What is inside the binary? And that's what we are going to talk about here. This is the program that we are going to compile, and we are going to see what is inside. It's a hello world, exactly what I was suggesting. So the first thing that we need is the compilation process. How the compilation process works? Well, we have our Go code and some mage is going to convert that in a binary that is amazing and all that stuff, all the cool things that a Go compile binary can do. And that Go binary, it's 1,852 kilobytes, 1.9 megabytes to simplify. So what is there? What is inside the Go binary? The first thing that you need to know is a Go binary is an ELF. And not this kind of ELF. It's an executable linkable format. I'm talking here about Linux binaries. This is going to be different format in Windows, and I think in Mac it's a different format. But at the end of the day, what you are going to contain is almost similar. So everything that you are going to see in this talk applies to other formats, or almost everything applies to other formats. It's more about the information that is inside, and it's going to be in Windows, and it's going to be in Mac. But I'm going to talk about specifically about Linux and the ELF file. And the ELF files is going to contain your program, all your program, or the executable code of your program, the executable code of your dependencies, and the executable code of the runtime. Apart from that, it's going to contain debug information and some metadata. And we are going to explore all of that during this talk. But let's start talking about ELF. We need to understand what is ELF before we start digging into the file. ELF is composed by a set of headers, and then a list of segments, a set of segments, and a set of sections. What is a section? First, I want to explain you what is a section. A section is a chunk of continuous data that is in our binary that represents something. Normally it's used by the linker, or the debugger. Can be used by the runtime also, but can be used whenever you are executing that. But there are sections that are used only by the linker or used only by the debugger. That's section. It's just chunks of data. And if you get this is at the bottom right corner of my slides. I always give you homework whenever I do a talk. So at the bottom right corner, what you are going to see is commands that if you execute, you get the output of that you are seeing there. Don't pay too much attention to this. We are going to go through all this during the talk. But what we see here is if I use readelf, I get all the sections in the binary, and we see that we have 23 sections. We are going to go through all of them and explain what they are for. Then we have segments. Segments is the bare minimum that you need to execute the code, because it's actually what defines what is going to go into memory whenever you execute the ELF file. The operating system is going to read the sections and put that sections in the memory. So that's the idea of the segments. So you have to understand that the sections is one way of organizing the data that is in the binary, and the segments is another way of organizing the data. But they are pointing to the same data. There's a lot of overlap between them. So sections and segments are pointing to the same data, but in different way, and the sections are for defining what data is where, and the segments are defined for what data goes in memory where. So if we use readelf to get the segments, what we are going to see is that we have 6 segments. We are going to explore them later. So we have sections and segments, and the first thing that you have in the ELF files is the ELF headers. The ELF headers is the metadata of the whole file, and then you have a set of headers per section and per segment. Well, per section and per segment and program are synonymous here. So when you see program, it's a segment. So the ELF files is just already 1,872 bytes are consumed by your headers with your hello world. And this is a ELF header information. You can see the interesting thing here is, for example, the entry point of the program. That is the first instruction that is going to be executed whenever you load the program for executing that. That you could think that is your main function, but it's not. It's an assembly code that is in the Go runtime that starts the bootstrap process of the runtime. And when all the bootstrap process finish, you start run your main function. But this entry point is pointing to that assembly function. Apart from the entry point, I can see here that we have where the program headers or the segment headers start, how many of them are, and how big are the headers. Also, well, you can see this is a segment header. In that section, you are going to see one header after another. And you can see here that the segment header is going to give you information like the virtual address, the physical address, the size that it's going to take in memory, the size that it's taking in the file, and some flags that decides if it's readable, writable, things like that in memory. So the next thing is in the ELF header. Also, we have the sections where the headers start, how many of them we have, and the size of each one. And the section headers is going to have metadata about the sections, like the name of the section, the type of the section, what is the address, size, flags, things like that. So now we have a very rough understanding of what an ELF file is. It's a set of headers that give you information about sections and segments, and a chunk of sections that are there and the segments that are there. It's just blobs of data. So let's talk about common ELF section. If you compile a Go file, you have certain sections. If you compile a C program, you are going to have certain sections. Rust, whatever language that compiles to an F files is going to have their own sections. But some of them are commonly used. One of the first one that you are going to find is the text section. The text section contains your code, contains the binary representation of the instructions, the assembly instructions that you are going to execute. And that is for your code, for the runtime, and for every dependency. So all the assembly code is going to be there. Actually, if you go here and execute an object dump of your program, you are going to see something like this. This is only a chunk of that, of course. And you can see, for example, that here we have a column that has some random numbers in hexadecimal. That random numbers are not random at all. They are the binary representation of the instruction that is at the right. And you can see here the memory address of that instruction. If you go and check where the memory starts in the section text and do some math, you can see that that instructions, that binary instructions, are right there in the file. I'm just taking the file, passing through XXD to get the hexadecimal representation of the file, and checking for the memory address that I calculated already here with this number plus this number is going to give me this number. And if I take that address, I get this here, the first instruction, and follow it by the following instruction. And this one will be the following here, and so on. So that's what is in the text section. It's your code, basically, once it's compiled, of course. Then we have the RO data. The RO data is a section that is very common in a lot of binaries. It contains the read-only data, and it's going to contain things like constants, or the literal strings that you have in your file, or the types information. Every single type have a representation that is going to be stored as part of the RO data, interfaces, another internal structure that the compilers write to help in certain tasks. For example, this is a chunk of the RO data. Of course, the RO data is big, so it's only a chunk, but I can see my hello world string there. So there's a lot of information in RO data, but one of them is your literal strings. Then we have data. Data contains read-write variables that are initialized. So if you have a global variable that is initialized, will be in the data section. Another one is the BSS. This is an interesting one because it contains non-initialized variables. And the BSS section in a Go binary, and almost in any binary, is going to be empty. Because what it's trying to represent here with BSS is that it's going to consume memory whenever you run the program, but I don't have any data to put there. So I don't need to store anything here. I only need to know the size that is going to take in memory, and the segments are going to take care of that. Another thing is the syntab. It's a symbols table that is going to help you to get information about the different symbols, like functions and things like that. Also, the string tab, it's going to have the string representations of the symbols in the syntab, and we can see a combination of that here. Well, we can see here the string tab, and we are going to see things like go.go is one of them, runtime.text is one of them. So there's symbols there that are represented as strings here. But we can, the interesting thing is if we go here and we read the symbols with readelf, what we are going to see here is that I have a lot of information on each symbol. All this is in the sim tab except for the name. The name is part of the string tab, but everything is there. And it's interesting that, for example, the symbol for go is a function, so the pointer here is pointing to the text section. But here is an object, and this address is pointing to the data section. So you have to understand that the symbol table is pointing to different places and give you the information about where that symbols are located. And the other one that is commonly seen, well, it's seen in every Elf file is the sh string tab. That it comes from section header string tab. It's again a table of strings for your section header names, because your section headers doesn't have the name stored there. It's have a pointer to the string tab, sh string tab, and this is the whole thing. And you can see here that you can see text and arrow data and string tab and others. So they are the string representation of the section headers. Also, another set of very common, commonly used sections are the dwarf information, the debug information. Of course, well, dwarf means debugging with arbitrary record format. That sounds like weird, right? But the reality is dwarf is a backronym. They have ELF, so the debug information, well, it's a dwarf. It's funny, it's okay. All this information is part of the debug information. All this section is part of the debug information. And it's taking 540 kilobytes, so it's a big chunk of, it's almost 25% of our binary. It's more than 25% of our binary. But we are not going to talk about that because Dwarf is a very well-known, very well-established format for storing debug information, and it will take me the whole hour to get into that. So I'm going to ignore Dwarf and let you know that that is for the debug information. But we are here in a Go conference, right? So we want to know what Go is putting in the binary. What is special about Go in the binary? So let's talk about specific sections that are included by Go and why some of them are there. One of the sections is Go build info. It's a very small section. This is the whole thing. And the Go build info is going to give you information about how the binary was built. For example, you can see here that the binary was built with SIGO enabled. Okay? Another one is node.go build ID. Again, a very small section. If we go to the binary, this is the whole thing, actually. And you are going to see this here is an identifier that is generated based on certain things, but basically it's a unique identifier of the build. So I can use the Go tool build ID to extract that same information, but this is reading the binary and this is using the tool. And also I can build my own binary using my own build ID, the one that I want. So it will be, if I run Go tool build ID, will be test in this case. And if I read the file here, instead of this, I will find test. OK, type link. Type link is another section that is, this one is interesting. It's a types table. It's a list of types, a list of offsets to the read-only data, offsets in the read-only data to the types in the system. So if we have X types, we are going to have X entries in this table that are going to point to somewhere in the arrow data. And something that is interesting is they are sorted by name. What you see there is just integers, but they are sorted by the name that the type that they are pointing to. And the information that they are pointing to is ABI type. ABI comes from application binary interface, and it's one package that is in the compiler. So the ABI type represents a type, and actually is this information here with the size of the type, the alignment, the string representation that is a pointer to the strings of the types, and things like that. So that is going to be a list of offsets to the read-only data where that types are. And we are going to see something interesting at the end about how type link is used in certain scenarios. ETAP link is kind of similar, but for interfaces. It's going to be a table of interfaces, and it's going to point to arrow data. This time it's by address, not by offset. And every entry is going to be an ABI ITAB. An ABI ITAB is going to have the interface that is implemented, the type that implements that interface, and some functions, pointer to the functions that are there. That's variable size, actually, even if there's like a one single array, but it's a variable size. And this is one of the most important ones, the Go PCLN tab. Go PCLN tab comes from Go program counter line number table. To be 100% clear, a program counter is the number that points to the current instruction in execution. It's saying, hey, I'm executing this specific instruction. That's the program counter. So what we want with the program counter line number tab is to transform from that program counter to the line number in our source code that is executing. And one of the main usage of the Go PCLN tab is to print your stack traces. But we are going to go deep in the Go PCLN tab. The Go PCLN tab is a structure that starts with a header. Then you have the func name table. There's a list of names of your functions. The CU tab, there's the compilation unit table that have a list of a list of offsets to the file name table. We are going to see how the compilation unit tab is used later. Then the PC tab that gives you information about specific program counters. So if this instruction, what's the line number, what's the file, things like that, is in the PC tab. And at the end, you have the func tab. That is a table where you have a list of PC to function, program counter to function, function information table, and the function information is right after the PC to function table. We are going to see in detail all that. This is the header of the GoPCLN tab, the first thing that you see. It starts with a magic number. That magic number, it's about the version of the format for the GoPCLN tab. Here we have this all F finished with a 1. That means that this header is from the version that the format version that is starting Go 1.20, if I recall correctly. The instruction size, the pointer size, where to start the text section, where to start the program. The number of functions that we have in our binary, the number of files that we have in our binary or have used in our binary, and then offsets to the function names, the compilation of units, the file tab, the PC tab, and the PCLN tab. So let's start with the first one, that is function named offset. Sorry, the function name table. The function name table is just a list of functions as strings. That's it. You can see a lot of different strings here, and all of them represent function names. Then we have the compilation unit table. The compilation unit table is a table that have pointers or offsets in the to the file name table. That is the next chunk of data that we have. The next chunk of data is the file name tab. The file name tab is just file names, one after another. And then we have the PC tab. The PC tab is going to contain program counter related data. If you have a program counter, you have program counter always. The current program counter can give you information about the stack pointer, the file name, the file that is executing that. It's not going to be the file name by itself. It's going to be a compilation unit index. The line number that is associated to, and if it's in line or not, and other data that can be related to a program counter, like PC data related. Then you have the func tab. The func tab is, again, a list for each function. We are going to have a program counter that points to the specific place where the function is defined, and a func info offset that is going to be pointing to one of these structures, that you have one per function. Again, you have this structure here, one per function, and this table is going to map from program counter to a function here. And in the function here, you have information like the function, where the function is located in the code. It's pointing to a point in the text section, or the function name is pointing to a func name in the PCLN tab. Things like the compilation unit index. The compilation unit index is going to be the index position in the compilation unit table that we saw before, that is going to point to the file name. So it's a bit convoluted, but it's a structure that is needed for giving you tracebacks. The start line, there's some things like the func ID that sounds weird, and the func ID is for mark special functions that needs a special treatment. You normally don't have that functions. Then some flags, things like that, okay? You have information about the function. An example of that, we have, for example, the first two functions here. The first function is the PC counter, the program counter is 0, and the offset is that number here. The first function, the function number 1, it's going to be in the PC counter 96, and it's going to be pointing here. So if we go to here, what we are going to have is this And it's going to say me that the entry offset for the text section is going to be 0 because the PC counter is 0 actually. The function named offset is going to be the first one that that is in the function names chunk of the Go PCLN tab. The function arguments is the number of bytes that is going to need for the function arguments. Things like that. The compilation unit index, the start line, the func ID is nothing, the flux is nothing now, things like that. So we have information about the functions. There's also other sections in the Go binary that I don't want to get too much into details, but I think it's interesting to mention them. One is the no PDR data. No PDR data is going to have it's going to store read-write variables without pointers. They are not going to point to anything. And the same for no PDR BSS. It's the same thing that BSS, but is ensured that none of the variables stored here is going to point to something else. And these two things are there to avoid the garbage collector to have to go through this data. Because if there's nothing pointing to somewhere else, the garbage collector doesn't have nothing to say about them. And then the Go Sync tab, it's going to be empty because it was replaced by the Go PCLN tab back in, I don't know if it was Go 1.12 or something like that, but it was replaced in the past. Now it's empty and it's there for compatibility reasons, I think. So now we have seen all the sections that you can have. From one side, you have the sections that are from general usage in the industry, and sections that are specific to Go, like the Go PCLN tab, the Go build ID, all that stuff. Let's talk about the segments. The segments are another interesting part of the binary. It's pointing to the same data. And actually, we have 6 segments here. And we can see that one of the segments is is a node segment that is going to take 64 in hexadecimal size in memory. That is exactly what it's going to take to store the node Go build ID information in the memory. Also, and you can see here that is have a flag that is R, that is read only. If we go to the next one, what we have is the text section and the node Go build ID. That segment is containing all this data. And what is important here is you can see here an E. That means that this section is going to be loaded in memory with the executable permission. So we can execute code that belongs to this segment. Also, we have the arrow data, type link, etab link, Go Sync tab, and Go PCLN tab that is going to be loaded as read-only. And finally, the Go build info, no pointer data, data BSS, and no pointer BSS, that is going to be loaded as read-write. So that is the segments. Well, we have a header at the beginning and the new stack at the end that are for making it compatible again. That's not very relevant for this talk. So some interesting things that I found while I was doing this, or some of them I did already know, but I think it's interesting to share them. We don't need all your sections. We have 23 sections here, and we don't need all of them. If I don't going to use a debugger, why in the hell I need dwarf? If I don't go to read the symbols table, why in the hell I need that? So actually, you don't need them. There's a command called strip that is not for Go or something like that. It's general, and it's going to remove all the non-needed sections for your segments. So if you are not using the section in your segment, it's going to be wiped, and it can reduce the size of my binary from 1.9 to 1.2 megabytes, what is nice. But I'm losing all the debug information here. What else? Another interesting thing, you can be leaking information without noticing it. If I take this readelf and I get -p that print the string and use the GoPCLN tab, take the GoPCLN tab section, I'm going to see this. I grab home and I'm going to see this. This is the place where I compile the binary. It's my home directory, my username here. So if you are very into writing malware or something like that, be careful with that, because probably your username in your machine may be similar to GitHub handle or something like that, and then you are screwed. So I'm not suggesting that you should do malware, but if you do it right, please. Another thing is the GoPCLN tab also contains all the information about file names and function names. So if you don't, if I get your binary, I can rebuild things like the whole directory structure and the whole function structures of your binary. And what I'm going to have is only the assembly code inside each function. But I can get a lot of information already about how your program is structured. So if you are into closed source, it's not my case, so I don't care that much about that. But if you are into closed source, maybe that is something to take into account. Another thing is your tracebacks are using GoPCLN tab information to give that information. All these function names that are stored in GoPCLN tab, the file names, the line numbers, all that information is stored to provide you tracebacks and rich tracebacks. So it basically, whenever you need to print a traceback, it's going to see the current program counter and start using the structures that are there to give you the traceback information. That's done by the unwinder, just in case you want to check it. Another thing that was cool was how reflect use, for example, type link info. Whenever you want to get a type by name using reflection, what it's going to do is going to here to the type link section, and it's going to start doing a dichotomic search, because the type link section is a set of links to type info that the type info have a file name, but this type link list is sorted by file name. Sorted by type name. So it's going to go to the middle, try to see the name of the type, and if that match is okay. If it doesn't match, it's going to check if it's bigger or it's more or less, and then it's going to go there and until it finds it. It's a dichotomic search. So that's interesting. Is how the type is one of the usage of the type link section. Yeah, a bit of a summary. As I said, there's a lot of information in the Go binary. Most of it is needed. Some of it can be removed if you are not doing debugging, but it's really hard to get rid of things like the GoPCLN tab. This is the whole binary. This is not at the scale, but it's more or less at a scale. You have the headers at the beginning, then the node Go build ID, then the text section that is a big chunk of our data. The arrow data is another big chunk because you have all the types, all the interfaces. You have a lot of data here. The type link and the ATAB link, then the GoPCLN tab is another big chunk of our binary. It's near 25%. The Go build info, the data section, the no pointer data section, the dwarf information, that is a set of sections actually, the SIN tab, the string tab, and the SH string tab. So that is what is inside your binary. And I hope now you have a better understanding of what each section here is for and why are there. Said that, I'm going to share some references. One of them is a video that is explaining in depth what ELF file format is. It's very interesting, and if you want to understand better how ELF works, it's a good video. There is something that I'm going to reference here, but it's not that helpful. It's the Go PCL tab design document that was written back then when the Go PCL tab was introduced. And it's not, it doesn't fit well with the reality, the current reality of the Go PCL tab. But you can understand more or less the intentions behind from reading the document. Well, from reading 3 or 4 times the document, because it's not light lecture. Then another one that is interesting is the Go Resim. That is, it's a Go program that allows you to play around with the symbol tables and with the Go PCL tab and other information that is inside the binaries. Garble, that's one that somebody mentioned me today, and I want to include it here. It's a program that allows you to reduce the size and remove things from the Go PCL tab and things like that. Also, if I'm correct, so I haven't seen that in depth, but I think it can remove information about file names and things like that. It can encrypt information about time names, about file names and other sensible information like function names. So it can obfuscate all that information to make it harder to have a clear vision of what is in the of the environment of building the program. And the other thing that I used for my for preparing my talk was reading the Go source code, especially in this case. I was reading a lot of the linker code and the runtime initialization for understanding how the file is generated and how then the file is loaded whenever we load our binary. Okay, another thing is the illustrations of this talk are made by Juan de la Cruz from the Penpot team. Penpot is an open source alternative to Figma. If you want to get the illustrations, you can get that in Penpot app. But the illustrations have a Creative Commons license, actually has a Creative Commons 0 license. That means public domain, so that's, illustrations are mine, but also yours, so do whatever you want with them. Another thing, a gift from Maramos. Maramos is the company that I work for, and it's they take the illustrations and did some stickers. I have a lot of stickers here. Just come here and take some of them. If you want an excuse to talk with me and ask me something, and just say, oh, you have the sticker or whatever, and I will happily give you a sticker and also answer you any question. And let's keep in touch. And that's it. Thank you. Questions?
Yep.
Oh, sorry.
Are there any questions? Yeah.
Be gentle, I'm a web developer, okay?
No worries. Have you maybe heard about the UPX package or software for reducing the size of the binaries? Have you maybe had any experience with that at all?
No, not really.
No, fair enough. Just
Is
a
it
question.
the UPX is a general package of a Go specific package?
General for everything. So
yeah, the problem that I foresee with that, maybe they have specifics for Go, but the problem is the Go PCL tab is something that you can't remove easily. You need to understand what you are removing, and you need to understand how you are tampering with it to reduce the size. Because if not, the runtime is going to use that. It's going to break something. Yeah. So unless that tool knows the specifics of Go, I wouldn't expect that reduce way more the binary, because the strip already reduced drastically the binary.
Okay.
Thank you for the talk as well. It was very fun. A question. I noticed that when you were talking about the segments that there are two segments actually defined as executable, one of them being .text, which makes complete sense, but another one is node go build ID, which doesn't. Do you have any
Okay.
idea why that might be?
To be honest, I don't know why that Go build ID is part of the executable section, because segment, sorry, because it's putting that together with the text segment, but I don't understand why. To be honest.
Okay, so if we are writing malware, that's where we should start from.
Sorry?
If we are writing malware, that's where we should start from.
Any other question?
Well, a classic one is how is this helpful for me? It's not. Okay. Don't worry, you don't miss anything. It's not especially helpful. It's helpful if you are into linkers and things like that, or if you want to shrink the binary really, really a lot. But in general, or if you are into analysis of malware or things like that, can be useful. But in general, this is not something that you are going to use as a Go developer.
Okay, so this is a variation of this question, and it's in the context of a back-end web application. What would be the advantage, and what would be like the disadvantage of stripping the binary and losing all the debug part?
Okay, if you strip the binary information, if you use a strip to remove the binary, the debug information from the binary, it doesn't going to generate so many problems, I think, because the debug information is for debuggers. Unless you want to have a debugger running in the server, it doesn't matter that much. I don't know how much of the current profiling, for example, leverage debug information, but I will say that the GoPCL and tab have enough information to provide that to the profiler. So I don't think it's needed even for profiling, but I'm not 100% sure. But I will say that in general, what you get is less size in the binary. Once it's running, there's no much difference, because what you are loading are the segments in memory. You are not loading the debug information unless you are using a debugger. So I don't think it's about the binary size. If you, for example, need to deploy that binary to hundreds of routers, for example, maybe you want to make that smaller or something like that. But in general, I don't think it's that relevant for a backend service.
Okay, thank you.
Or for distributing the, if you have a big program that takes 200 megabytes, maybe if you strip that, you save 30 megabytes. And if that is distributed to millions of users, that adds up a bit.
Hi, Jesus.
Yeah,
Thank you for the talk. Regarding the question, the perf Linux standard tool uses the dwarf section to recover the name of the functions. So if you strip the dwarf section, you obtain less accurate perf stack trace.
Okay. Yeah, no. For Linux tools, for external tools that are not related to Go, all of them are going to rely on things like the symbol table and the debug information. For Go, internally in Go, there's a lot of things that are resolved with the Go PCL and tab because it's already there and it's already loaded in memory. It doesn't make sense to start loading other information. So, but yeah, for things like anything that is external and is going to use the standard set of sections that you can see in an ELF file, it's going to stop working. It's going to start giving you memory addresses instead of the file names and instead of symbol names. Oh, okay. Well. Any other question? I can repeat the question if it's needed, so that's not a big deal. Any other question? Once? Twice? Gone. Okay. Thank you, everybody.